Good morning. So there's some caveats I should tell you for today's lecture. One caveat is that I was really not kidding in the introduction when I said that there are hundreds of papers on this subject. This is only a very small piece. It is the piece that I consider most basic and perhaps even most useful. But there's a great deal of other work which I'm not going to cover and which could easily be useful for various tasks. So once again, if you have questions during the talk, feel free to ask them then. Oh, Dinaj, you made it. We are all kinds of organized for this lecture. Dinaj actually printed out and copied slides. So not only are they on the web, they're also in your hand shortly. Okay, so what are generalization bounds? So first of all, we need to start out what learning is. And a reasonable understanding about what learning is it's acquiring prediction ability. So the process of learning is the process of acquiring your ability to predict in the future. So if you think about this a bit, you realize that, in the worst case, you can't do this. You could have an adversary that knows the process that you're using to learn and just chooses to screw you every time. But, maybe in the real world you don't always have an adversary. And then the question is, how can we even analyze this? And one very common way is you assume that you have independent examples that are each coming from the same distribution over and over again, right? And then it becomes possible to actually predict, because doing well in the past means that you have some reasonable expectation of doing well in the future. So the mathematics I'm talking about today is how doing well in the past gives you some reasonable expectation about how you do in the future. So the thing to understand about this is that it is significantly different from my other lecture in that we're assuming independent examples, independent and identically distributed examples, in fact. So this is something that I think is kind of critical to properly understanding the mathematics. You have to really watch the assumptions, right? This is an assumption of independence, and what that means, this applies when your examples are independent. In practice, often, your examples will not be independent. Sometimes they will be, or at least close enough to where we can use the same math. So this is something with a more limited scope than what I talked about last time, but it's answering a question that cannot be answered without making some assumption about how the past relates to the future. And independence is the standard way of doing that. Yeah?
So is this first bullet, is this directly related to the no-free lunch theorem?
Yes. So the question is the first bullet the same as the no free lunch theorem? And the answer is yes. So the no free lunch theorem is kind of this stated in a Bayesian way. If you just think about it in an entirely adversarial way, it's a trivial statement. Okay, so why do we want to study this? So maybe if we study this, then we get better methods for learning and actually for verifying our predictive ability, right? So maybe if you're working on the space shuttle or something, your boss wants to know that the things you predict are actually going to work pretty well in the future. So maybe you want to actually have some technique for coming up to him and saying, here's a certificate which says I have successfully learned to predict when O-rings will fail. And maybe you want that certificate to be, pretty darn ironclad. So the things I'm talking about today give you some mechanism for doing that. Right. So better methods of learning. So when people are faced with this problem right now, what they typically do is they take, if they have a bunch of examples in front of them, they take, the first 2/3 or whatever, or the first all but 100, and they train on that, and then they test on the last 1/3 or last 100 or something like that, right? So we divide things into a training set and a test set. We train on the training set, we test on the test set, And then the hope is that maybe we can actually do better. There are other techniques, which I'll be talking about today, for giving you a proof of the same degree of validity as, I observed a good test error rate. And actually a better degree of validity in many ways. And then the other thing that you get when you look at this is you learn a little bit about how learning algorithms should be designed. So in particular, we can look at these bounds. We can go, oh, look, there's overfitting. So Rob Nowak actually showed some good examples of that yesterday. And then when you know what overfitting is, maybe that can help you with learning algorithm design. Maybe you can get a better mechanism for pruning decision trees. Or maybe we can think about why exactly large margins are good. And there's another example, sparsity, right? So if your learning algorithm depends upon only a small subset of the training examples, it turns out that you can state a nice generalization bound. All right, so these are the motivations. And then this is the outline. I'm going to go through the basic model that I'll be working with. And then exactly how you use a test set with a bound. How you get a bound on the deviations in a test set. So as I said, this is the most basic. And you'll see the mathematics is very basic here. And I think this is the simplest. This is the simplest bound which exhibits what exactly overfitting is. This is Occam's razor bound. And then this is maybe a little bit more advanced. This is the Pack-Bayes bound, which is a slight generalization on the Occam's razor bound, which has some nice applications. Okay? So, the model. The model is much like you've seen. You have an input space, you have your binary output space, you have your classifier, and then we're doing this. This is what's different from my previous lecture. We're making an assumption. This assumption, by the way, I should mention this. Independence is a real assumption in the sense that you cannot verify that your samples are coming independently. You can verify that they're not coming independently by saying, look, it's 0, 0, 0, 0, 0. That doesn't make any sense. It's got to be. But you cannot verify independence in an efficient manner. To even think about verifying independence, you would need to have a number of samples which is proportional to the size of X. And that is not going to happen for almost all applications of learning. So all of our samples for all of this talk come independently from the same distribution. And what exactly M is, that varies from bound to bound, but everything is coming independently. Okay, so since we're only doing classification, and since we're only going to be worrying about error rate, this is a more compact way of specifying the error rate, right? So this is the error rate of classifier C on the distribution D. And that's just thing you're familiar with. It's the probability that the classifier is wrong for random draws from D. And of course, we're not going to assume that we know D, because that would be assuming that we know the solution. Instead, we're just going to know some sort of approximation in the form of independently drawn samples S from D. Let me try this technology. Ooh. Right, so S is independently drawn from D, M times. And when I say, oh, I see, there's a normalization issue here. So there should be an M here, because it's M times the probability equals the sum of the indicator functions. Right? So when I say X and Y drawn from S, I'm just saying uniform distribution over S. So this has a lot of different names depending on how exactly it's used. This is your proxy for the true error rate. And it's called the training error, or the test error, or the observed error. And exactly what term you use depends upon the context. Right. So this is just a note about what that means. Okay, so very basic setup. And now we need to start asking ourselves some questions. So it turns out you can exactly specify the distribution of this observation when you know the true error rate. It's a binomial distribution. So maybe I can actually show you what that means. Ooh. So the black there is what a binomial distribution looks like. And the mean of the binomial distribution is right on the red line. Okay? You can see that it kind of gets more Gaussian-like in the center, and it gets more peaked and skewed towards the edges. Here you can even see it better. Oh. So this is the fundamental distribution we're working with. It's something which near 0 or near 1 becomes peaked, and which in the middle is approximatable by Gaussian pretty well. Okay. Ooh. Ooh, too much. Okay, so binomial distribution. And then how do we use this observation? Oh, you've already seen the video, so the picture doesn't matter so much. Okay, so the way we use this is by thinking about the cumulative distribution of the binomial, right? So this is the probability, that M should go away. The probability that the observation is less than k, right? So the number of the number of heads or the number of errors that you observe for your classifier is bounded by k. And that's just going to be the sum of the binomial coefficients, right? Sum of the probabilities of each individual event. So as far as the pretty picture goes, let's see. What this means is just we're going to be cutting things off and computing the area down here, right? So the thing which is kind of rough about these binomials is that you don't actually know what the true error rate is, right? So since you don't know what the true error rate of your classifier is, we don't know C sub d, we have to somehow get rid of the knowledge of that. And the way that you get rid of the knowledge of that is, a technical term is using the pivot of the cumulative. So in particular, you ask yourself, what is the largest true error rate such that the probability of observing k or fewer heads, k or fewer errors, is at least delta? Okay? So if we go back to here, if the green line is k, and we have some very small delta, I think it's delta is 1 over 100 or something like that here, then the red line is that maximum, right? So that is the particular p which achieves this maximum. And we can compute, as you can see, this is easily computable. Okay, so that's the basic model, and a few observations about the basic model. And now we want to go and we want to actually compute various bounds, because that's the business we're in. So we have our standard technique where we take our data and we cut it into the training set and the test set, train on the training set and test on the test set. And now maybe instead of reporting the test set error rate, we want to report some sort of confidence interval. We want to say, well, in the future, we expect that, our error rate is not going to be too large. And we need to quantify exactly what we mean by too large. So there's a very simple bound which applies here. It says that for every classifier C, for every distribution D, for every choice of confidence, the probability over a random draw from the samples, or random draw of the samples you see, that this pivot of the binomial distribution is greater than the true error rate is greater than 1 minus delta. Right? So that says that the particular P. So what you're doing is you're looking for the worst case true error rate such that you have a reasonable probability of getting your observation. Right? And that's exactly what the max is doing, and this is the answer that you get. So the proof is very easy. You just say, look, with probability of 1 minus delta, our observation is not in our tail of size delta. And so, by the definition of this bin bar, this quantity will be greater than the C sub D. Okay, so let's go back here and look at this. So this is doing that computation, right? So we get this observation, and then we compute our confidence interval, and that's what the red line is. And we can just do this easily, no matter where we are. There's some very subtle things here which I think we should talk about. Whenever people think about bounds of this sort, there's a very common failure mode. What they do is they say, well, with probability 1 minus delta, my error rate will be less than this bin bar in the future. And that's not the right way to think about it, because it's not what it says. This says that this isn't randomizing over the future. This is randomizing over the past, right? So, in particular, if you have Bayesian inclinations, you tend to think of this as a fixed variable, but this is a random variable for this analysis. And you have to keep that in mind when you're interpreting the statement. What this says is not, okay, what would be false is the probability that I have an error rate greater than this is less than that. That would be wrong. What would be correct is to say that if you use this test set bound in the future on independent samples from multiple times, then the proportion of the times the bound will be wrong is 1 minus delta. So it sort of doesn't say something about your individual error rate. And it's easy to actually violate this. I'll mention it in a sec. But what this says is that you have some mechanism which will not fail you very often for evaluating bounds. So if you're the government and you're evaluating drug companies, this says that the drug companies cannot cheat too much, right? Because you know that they do want to cheat. Actually, they have some clever techniques for cheating. Let me tell you how you can cheat a little bit, right? So this is the secret dart art. This is the dark force, yes. So one way that you can cheat is you can draw twice, right? You draw two S's, and then you evaluate and you take the best one, right? That's cheating. So drug companies do this, right? They run two studies, and then they report the results of whichever one turns out the best. And they got discovered doing this, and they got their hands slapped. So that's one way you can cheat. And the bound's just not valid if you do that kind of thing. Okay, so hopefully we're clear on the meaning. If there are any questions, then feel free to ask. So this proof actually has a nice graphical way to think about it. What you do is you say, I don't know what my distribution is. It has some true error rate, which you can't see, right? So there's some true error rate here, which is inducing this binomial distribution. And there's some true error rate here, which is inducing the purple binomial distribution. There's another one for the yellow. But whatever my true error rate is, I'm going to exclude the possibility that I'm in the tail, right? So this is the tail of size delta. And then I'm going to get some particular observation, and then I'm going to throw away all the possibilities which are excluded by, this is in the tail of that blue binomial. So it's not allowed, right? Because with probability 1 minus delta, we're just not there. And then you have a set of possibilities. There's the purple, and there's the yellow, and there's everything in between, and over here, and so forth. So you just go, well, what's the worst one, right? So this is the graphical form of computing that bound. Okay. So there's some things to note about this. It's extremely satisfying in some ways. First of all, there is no chance you'll be able to improve on this when you have this particular setting. You can, in addition to bounding in addition to upper bounding the true error rate, you can also lower bound the true error rate using the same technique. And the use here is sort of verification of learning, right? So this is one technique. You go to your boss and say, look, the O-rings are not going to fail very often. Right. So there are some difficulties with this, which is that people don't naturally intuitively know what bin bar means. Maybe it helps if you have little pretty pictures of animated, but there are approximations to this bin bar, which you will often see if you go and you look at the literature for bounds. And many of these approximations use a technique which Chernoff started, this exponential moment method. And in particular, he applied it to binomial variables directly. So, right, what does this mean? So let's start here. For every classifier C and for every distribution D, you can say that the true error rate is bounded by the average training error rate, or average test error rate, plus this square root log 1 over delta divided by 2m. And that should make some sense to you, because this is basically saying we have a Gaussian-like quantity, right? And if you go and you look at the pretty picture, you see, ooh, it's a Gaussian-like quantity, especially in the middle. So when you're over near the edge, the bound becomes very loose, because you can see that the distance between the green and the red is smaller than it is here, right? But, you always lose a bit with approximations. And then up here is a tighter approximation. So I'll show you which one that is. So the yellow, which is right there. Right, so the blue is the square root approximation. You can see how it becomes very loose over here. And the yellow is the relative entropy approximation. So it behaves maybe a little bit better. It's always a bit, it's never worse than the square root approximation, but it's still not quite as tight as the actual exact computation. Okay, so what is this thing here? So KL divergence is who knows KL divergence here? Oh, good number. Okay, so this is the KL divergence between a coin of that bias and a coin of that bias. And what should I say? For those who don't know the KL divergence, it has an interpretation in computer science. The KL divergence between Q and P is the number of extra bits that you need to encode the output of a source, which is generating things according to Q, but with a code optimized for P. Right, so if you have a source, then you can the minimum number of bits you can use to encode the source is just the entropy of the source. But if you have a code which is mismatched, this is the penalty due to the mismatch. Where Q is the reality and P is what you created the code for. So it's interesting that I guess that information theory comes up in learning theory, and you'll see some more of that later. Okay, so here's an example. We can say, suppose delta is, ooh, wow. Shouldn't be shooting myself in the eye. Suppose delta is 0.1, so we want things to be correct with, we want the bound to hold probability 0.9. Suppose we have 100 examples, and suppose we observe 2 error rates in our test set, 2 errors in our test set. Then the square root turn-off bound gives us this interval. So I've actually taken the delta and I've allocated 0.05 to computing the upper bound and 0.05 to computing the lower bound. And the exact calculation gives us this. So I have another little program, which we should do. Right. So here's your opportunity to break my program. What is a good bound error rate? Should be more than 13? 30. Whoa. Yeah, bound error rate of 30 would not be so. You want 30 examples? Okay. That's too easy for me. But bound error rate, what's a good bound error rate? 0.2? Okay. Yeah, and now you had some statement about number of examples, but 30 was too easy, right? Oh no, you can actually get by with less. Yeah, let me plug in 10, and then we have number of errors, right? That's the other quantity. 9. That's the boy we suck off possibility. How about 1? Because it's a complement of 9, right? So it's the same computation, but sort of the other direction or something. Right. So there we go. 0.27, right? So our bound on is 0.27. So anybody else have numbers they want me to plug in? We can try the 9, but it won't be so satisfying. All right. So if you're computing the lower bound on 0.2109, that's equivalent to computing the upper bound on 0.2101, because you can just 1 minus the bound. All right. So I feel like maybe we should do something a bit more impressive. What do you know? It works. Okay. Say again? This is the calculation of bin bar.
Beyond the mean, as it positive 0.001, and I also 0.001 to negative side also. So you will be getting an area of 95% in your normal distribution.
So the confidence is 0.2, which means that with probability 0.8, the bound will hold for future evaluations. right? And we're explicitly not approximating this as a Gaussian. Instead, we're actually doing the exact calculation for a binomial distribution. So let me show you some about why you want to do that. No. Too much. Okay, so let's compare. So there's a very common approach, which I would like to dump cold water on. So the very common approach is you say, well, a binomial is kind of like a Gaussian. So what I'm going to do is I'm going to approximate it by a Gaussian, and then I'm going to compute a confidence interval for a Gaussian, right? So if k is the number of test errors and image number of examples, this is your observed mean, and this is your observed variation, and then you can compute a bound, which is maybe this k over m plus 2 sigma, which gives you about a 95% confidence interval for if this was actually a Gaussian. And the question is, how do these actually compare in practice? So, right, we did a few calculations. So take a bunch of data sets, cut them up into training set and test set, and then on the test set, go and compute these various bounds. So let's see, how does this work? For each test set, there are 2 bars. The one on the left is the test set bound that I just described, and the one on the right is the Gaussian approximation, which I just described. And you can see a few things, which are kind of odd. So over here, you see that the Gaussian approximation says that your error rate is less than 1.5. So this is not very satisfying, of course, because it's like saying, suppose I flipped a coin, I will get less than 1.5 heads, right? Another thing which happens, so these data sets, so for this data set, it was very, very tiny, which means that the size of the test set was like 2 or 3, right? And, we observed 0 errors, right? So if you observe 0 errors with this Gaussian approximation, something horrible happens. Right? So if this is 0, then this will be 0, and that means this will be 0, right? So you just try to fly the shuttle, and it'll blow up because you're overconfident. But on the other hand, for the test set bound calculation, it takes into account the number of examples in a very explicit way, and so it gives you something much more reasonable. It says maybe you want to run a few more experiments. However, this data set, which just turns out to be very easy, it's also large. So it's large enough to have a large test set. And that means that both bounds, the error it observed for here is 0 again, and both bounds are actually very near, or one is 0 and one is very near to 0, which is appropriate because you have a lot of test examples and you did well on each of them. Okay? So what's happening is we're not getting this weirdness where our bound is above 1, and we're not getting overconfident. This is maybe the most important part. So if you want to go and evaluate some sort of binomial confidence interval, I really think you should just use the binomial confidence interval. That's just saying what I just said. So we can think about the process of evaluating these bounds as a game. In step 1, a learner chooses a classifier. And in step 2, the verifier, so that's the drug company, right? They choose their drug. And then in step 2, the verifier, which is maybe the government, goes and says, oh, here's a study where we're going to, we grab some people, we test the drug on them, and then, we see how well it works. So this is the valid order of operations for this particular bound. If you get these out of order, things fail. So in particular, if the drug company draws the examples and evaluates the bound, it does it multiple times before choosing which one to report, then that's bad. All right. So I call this an interactive proof of learning, but it's kind of interactive in the trivial sense. The only thing that's important here is that the choice of classifier comes before the examples are drawn. So there's another slight variation on this, which is very commonly used in machine learning. It's k-fold cross-validation. So what happens in k-fold cross-validation is you have m examples, and instead of dividing into a training set and a test set, you divide it into k equisized sets. So, and then on each set, you train on everything but that set, and then you test on this held-out subset, right? So for each individual run of this is like a train and a test on a set of size m over k. This is not well understood theoretically. The best result we have is that the confidence interval should be smaller than for a test set bound of size m over k. Now in practice, this often works much better. But there are worst case choices of distribution in learning algorithm such that this bound is actually realized. So what this means for you in practice is that leave one out cross-validation, where k equals m, you should not trust too much. It is possible to actually severely overfit easily with leave one out cross-validation. There are some learning algorithms which are stable in some sense where this is proved to work. But for general learning algorithms, it's not proved to work. Anyway, there's a big open problem here. And I've thought a bit about trying to solve this, right? So maybe it's possible to state much tighter bounds if you go and you look at how much the different classifiers that you learn on the different k-folds disagree with each other, right? So the bad examples are always ones where they disagree with each other a lot. Maybe if you just look at them and you say, look, they agree almost all the time, you can state a tighter bound. But it's a very difficult analysis. I would say don't try to do that unless you feel very overconfident. All right, so are there questions about cross-validation? Yeah?
Can you identify some of the biggest problems with trying to do this analysis?
Oh, trying to do that analysis? Yeah, the big problem is that things are not, the individual estimates are not independent. They're dependent. And tracking those dependencies is very tricky. Maybe I should mention exactly one way that leave one out cross-validation can fail horribly. So here's an example. Suppose I have a learning algorithm. The learning algorithm is the following. It takes a look at the examples, and it says, if there are an even number of ones, I'll predict 0. And if there are an odd number of ones, I'll predict 1 all the time. Right? So it's either 0 all the time or 1 all the time. Now, suppose we have a distribution which just picks label 1 with probability 0.5 and label 0 with probability 0.5. Right? So then maybe we end up with, I don't know, 46 heads, right? So if we hold out a tail, we end up with 46 ones. So if we hold out a 0, then we're going to predict correctly because it will just the parity will be even. If we hold out a 1, then we'll also predict correctly because now the parity will switch to, there's 45 heads, 45 ones. So we're going to predict the guy that we held out perfectly. Right? So what that says is that although our error rate is 0.5, the observation that we'll get from leave one out cross validation is, 0 errors. Yeah?
So why not just use Bootstrap?
Why not just use Bootstrap? Right. The state of analysis of Bootstrap is still not quite satisfying. It's not as good as for the test set bound. I think we should talk about that later. Okay. So that's the test set bound. That's the basics, which I think everybody should know about these things. That is the practical part which can be used now. These next things are hopefully give you some intuition about good learning algorithms and so forth, but they're not directly used that much yet. I guess Rob Nowak yesterday was talking about a variant of the Occam's razor bound, which is getting pretty near to use. Okay, so the first thing is why you will find, as you go out in the world, that the test set bound works great in practice. And the question is, why do we expend 100 papers on trying to do something other than the test set bound? It's a good question, and it actually has some pretty good answers. One of them is that there exist learning problems where the process of taking the training set, taking a big set, cutting it into training set and test set is very, very bad. In particular, taking out these few examples for the test set can destroy your ability to learn. And in fact, you can imagine learning problems where taking out just one example destroys your ability to learn. So let me tell you, the example where just taking out one is very bad. So the example is learning a parity of a subset of the bits, right? So the target, the label, is a parity of a subset of bits. You have a set of bits for your input, right? The way to learn this, when you have no noise, is to use Gaussian elimination. So you just think of your examples as forming a matrix, and you use Gaussian elimination to figure out which bits are the critical bits. And if you have a number of examples which is less than the number of features, you lose. Your error rate is 0.5. And if you have a number of examples which is equal to the number of features and they're independent, which they are with probability 0.5 or so, then you win. You get it perfectly. Now, this is kind of an extreme example, and you may not believe that you have parity in the real world, but it is observed that there are phase transitions in how well you can learn as a function of the number of examples on a lot of natural learning problems. So this is a real point. The other reason why is because you want to use these bounds to really guide how you learn. What classifier do you choose? You can't do that very well with test set bounds, because the process of guiding learning implies evaluating a lot of different classifiers, and setting aside a separate pool of examples for each classifier you evaluate is the kind of thing which will result in very bad judgments, because you'll take all your information and your fraction into very small sets and just not be able to predict very well in the end. So this is what motivates training set bounds. So training set bounds are bounds where we just have one big training set. We learn the training set, and then we compute a bound for what we learned. There's no cutting anymore. So this is the interactive proof of learning associated with the Occam's razor-bound protocol. What happens is your learner first chooses some prior over classifiers. So this is a prior in quotes because it's not a Bayesian prior. It's just some particular normalized measure over classifiers. So if you were Bayesian, then you would be expecting a distribution over distributions. This is a distribution over classifiers. Right? So we commit to a distribution over classifiers, and then we draw training examples. The verifier draws them, gives them to the learner. The learner chooses some classifier, and then the bound is evaluated. So the choice of classifier can be dependent upon how the bound will be evaluated, because this is just a deterministic process at this point, right? So for the Occam's razor bound, it's okay to sort of reuse the examples over and over again in your choice of classifier. Okay, so the Occam's razor bound says for every choice of these priors over classifiers, for every distribution, for every choice of confidence, the probability that for every classifier, the true error rate is bounded by this quantity is high, right? It's 1 minus delta. So, corollary. So the only difference from the test set bound is that delta has gone to delta times P of C. And that's it. That's the only difference mathematically. So I think yesterday Rob Nowak was working with this kind of result, which is just taking this and using the turn-off approximation. So he had a description length, but you can think of a description length as is also a measure over classifiers using this Crafts inequality. So you can say that the probability of a classifier, according to the prior, is 2 to the minus description length. And as long as you have a good way of describing things, that's a valid choice. So this proof is slightly more complicated than for the test set bound, but it's only 1 page. It's very easy. First of all, you start with a test set bound. And instead of plugging in delta, you'd plug in delta times P of C, because this is valid for all delta, right? So this is the delta times P of C is the delta in the test set bound, which means we have the delta times P of C there. Then we just negate this. So it's just a matter of working out what negation means. So this is something happens with high probability, and now something happens with low probability. With the opposite happens with low probability. Then we apply the union bound. The union bound says that the probability of A or B is less than the probability of A plus the probability of B. Whoa. DeVore, you need to fix that? Uh-oh. A little bit too energetic for my cybernetic enhancement. Say again? Yeah, it could be. I'm just trying to distract you. Ah, yeah. The mathematics strikes back. Right. So we use this union bound over and over again, and that gives us a sum of these delta times PFCs. And PFC, the sum of the PFCs is 1 or something less than 1, in which case we can just put in delta instead. And then, of course, you just negate again. Right? And then that gives you the Occam's razor bound. Okay, so in pictures, what this looks like is you have a bunch of different classifiers, and they each have a different size cut in their tail, right? So the size of the cut is delta times P of C, so it varies from classifier to classifier. So this classifier has a very small P of C, and this classifier has a larger P of C. So just the area equals delta times P of C. And once again, you don't know what the actual error rates of the classifiers are. So we just kind of go through the same analysis that we went through for the test set bound. So our learner chooses some classifier. That classifier has a specified size for delta times P of C. That's what the red is. These areas are supposed to be the same. And then you don't know what the true error rate is, so you just choose the worst one, right? The worst one consistent with not being in the tail. Okay, so let's go back a little bit. So the key difference, aside from this here, is we have for all C inside of the probability. And that means, since it holds for all C, it holds for whichever C your learning algorithm happens to choose. And that means you can evaluate, you can use this bound over and over again in the process of learning itself. So I think Rob talked about overfitting yesterday, but the way that overfitting is expressed here is if you have a very complex classifier, this P of C is going to get very small. And that means your bound is going to get very bad because delta times P of C is going to get very, very small. So this gives you some way of trading off between the two possibilities. Right. Example. So everything is the same as before, except now our P of C is 0.1. And now we can go and we can compute the square root turnoff approximation, which gives us this confidence interval, which has an unsatisfying, we will observe no more than, how do you think about that? Well, anyway, you shouldn't have a number of heads, which is minus 0.143. And if you do the exact calculation, you just get something a bit tighter, which is always within the interval from 0 to 1. All right, so once again, we can go and we can actually apply this to various learning algorithms on various data sets. The particular learning algorithm will be some sort of decision tree. The probability of failure will be set to delta. All the problems are sort of discrete problems from this UCI database of machine learning problems. And then there's two things I'm going to compare. One of them is the train and test approach, and the other one is the train and everything approach, right? So the train and test approach, I'm just going to look at the test set bound. And on the train and everything approach, I'm just going to use this Occam's razor bound. Oh, one other caveat, which is very important. Another horrible, horrible way to cheat, which is very hard to catch, is in your choice of data set, right? So I will tell you that I chose the data sets before I evaluated everything, and I'm reporting all of the results. You should do that too. All right, so this is the results. So you have a test set bound, which is the left here, and you have a Occam's razor bound, which is the right. And the code which is being used here is something very like the first code which Rob talked about yesterday. So there was a question yesterday about how the constants work out, right? And this direct comparison can maybe tell you something about how the constants actually work out. What you see is that the Occam's razor bound is typically a little bit looser, right? So forth. It's not a lot looser. It turns out that it's quite a bit looser here. This is a pretty large data set in terms of number of examples. So there's maybe a factor of 10 there. Another thing, of course, to keep in mind is that the training set is about 5 times larger than the test set here. Sometimes this Occam's razor bound is actually winning. So over here, it wins. These are not very impressive confidence intervals. What's happening is the number of examples in the test set is small. And then it becomes very important that we actually have 5 times more examples in the training set, even though multiplying by PFC makes things a bit worse. Yeah?
Is all of this to your choice of measure over what you're learning, the P of whatever?
How sensitive to the choice of what?
When you use Occam's razor, you're actually doing model selection, right? I mean, that's basically why you're putting a prior probability of some sort or another on everything that you could possibly measure. And I mean, if I wanted to do that in an algorithm I just made up, I wouldn't really know how to assign that necessarily. I don't even know how many possible things there would be for me to learn in total. So I'm just wondering how sensitive all of this is on that.
Right. So the question is, how sensitive is it to sort of your choice of learning algorithm, right?
Choice of ranking over the algorithms, where you assign some kind of measure to each possible. It's what allows you to apply the union bound. The P of whatever.
Okay, so
Find that, how sensitive is that in this analysis?
right. So the question is, how do you define PFC? And the answer so far is you do some soul searching. Right. How sensitive are the results to the actual choice of PFC? And the answer is it can be quite sensitive at times. So in particular, if your choice of PFC was just a uniform distribution over all classifiers, that would be very bad. It's important that your choice of PFC be sort of well aligned with your algorithm if you want these bounds to be tight. So in particular, the pruning process here chose the classifier which minimized the bound according to the particular choice of PFC. So minimized amongst the prunings of the tree that was grown. I wish I had a good answer for you. Think hard is not a really great answer when you want something to actually work out. I think that's an honest evaluation of the state of things right now. I can't hear you.
If you have a C that is a continuum of possible classifiers, PFC will be zero.
Right, right. So if you're doing some sort of continuous set of classifiers, then PFC will be 0. And then, of course, the Occam's razor bound is not going to tell you anything useful. So one thing to understand with these training set bounds is that these are bounds. They're not... let me say this another way. You could take the same learning algorithm. You could plug in the P of C, which is uniform over all possible decision trees. The bound would be horrible, but your performance would be exactly the same as here because it's the same learning algorithm, right? So just because the bound says you have a horrible classifier does not mean that you have a horrible classifier. And that's something to always understand about bounds. So this particular bound will not apply in a strong way when your P of C is over a continuous set. Let me tell you two things. First of all, the Pac-Bayes bound will apply there. And second of all, there's these VC bounds, which I will not be talking about, that apply there to some extent. You start to get into issues of it's very difficult to avoid issues of how tight is the bound when you start working with continuous sets of classifiers. Yeah?
Bring this bound because we are working on a biased estimator.
Are we constraining these bounds because we're working only with biased estimators?
Are we considering these all bounds like it's a tight bound or a loose bound? Only because of like just trying to figure out the question.
Just trying to characterize.
Yeah. As it is, are we going for an unbiased estimator of this particular bound or a biased estimator of the bound?
Right. So in statistics, there's this notion of an unbiased estimator, right? And these are not unbiased. These are pessimistic, right? So these bounds are supposed to always be a bit worse. This test set bound may be, you can prove that you can't do anything better. But for the training set bounds, it can often be the case that a different training set bound will actually do much better. Right? So there's this example of the uniform distribution over all classifiers versus some reasonable description language. The distribution induced by some reasonable description language. Okay. I think it's time for a break. Let's take a break for about 10 minutes.